Okay, so welcome everyone back. Today we are happy to have Andrew, who's going to tell us about higher representation theory and coordinate Heegaard Floer homology. Yeah, thank you for joining us.
Great. Thank you very much to the organizers for inviting me, and thank you all for coming. I'm going to talk about something that's related to joint work with Raphael Rouquier that's just appeared on the archive as of a couple months ago. Project that was in development for a long time, and I'm very pleased it's finally available. I've given several talks recently on the sort of meat and potatoes of that paper, of the constructions of this tensor product operation that we define, and then the theorems that we prove in cornered Floer homology using this tensor product operation. So today I wanted to do something slightly different. And so I did see, this is slightly motivated by a conversation I saw on the Facebook wall of John Baldwin, where some indeed Berkeley faculty were discussing topics that are in some sense related to this talk. So I hope, well, I wonder if Vivek will show up, but we'll see. But so I wanted to start with, you know, semi-expositional sort of idiosyncratic overview of how I view things, maybe especially from the little bit of physics perspective that I know. And then I want to sort of sketch an alternate way of looking at Heegaard Floer homology. So if you don't know what Heegaard Floer homology is, that's okay. I'll say a bit about it in this talk. But the goal is less to summarize the results of these of this paper with Raphael and more to propose an alternate way of looking at some things that are often, seem a bit mysterious and get questions asked about them on Facebook, that sort of thing. Because I think the current understanding of it, well, it's missing a few things. That's what I propose. So we're going to start with some background, though, and the background is going to start with Witten's paper called Topological Quantum Field Theory in the 80s. And so a big thing in the 80s was this work of Donaldson and Floer in low-dimensional topology, these instanton invariants. And Witten explained this work in terms of a particular quantum field theory, topological twist of a supersymmetric Yang-Mills theory in 4 dimensions. And this is what's so-called topological quantum field theory, a Witten-style topological quantum field theory. And that more or less means the correlation functions don't depend on a metric on the 4 manifold in question, at least on most 4 manifolds. Maybe with small b2 plus, it maybe does depend on a metric or a conformal structure or something. But for most 4 manifolds, this is actually metric independent. So this sort of thing is interesting for math and was interesting at the time because there's this problem of telling apart smooth 4 manifolds that are homeomorphic but not diffeomorphic. And most invariants are pretty bad at this. The invariants will be the same if you have homeomorphic manifolds. But these Donaldson invariants actually are able to tell apart non-diffeomorphic but homeomorphic 4-dimensional manifolds. So that was one major reason for interest mathematically. Physically, as far as I understand it, at least reading what Witten says in these papers, this is a priori something that one might think could be related to quantum gravity because you're looking at a quantum field theory where you have metric independence in a really interesting, non-trivial way. So one can ask, though, okay, from the mathematical point of view, does this physics let you do anything new mathematically? And this, well, is answered majorly in the affirmative by work of Seiberg-Witten in 94. So by looking at this n equals 2 gauge theory that was underlying the Donaldson theory, they were able to get new invariants for smooth 4 manifolds, probably encoding more or less the same information as the old ones, but fundamentally based on abelian gauge theory rather than on non-abelian gauge theory. That made them much easier to work with, but you could prove all of the same impressive theorems with Seiberg-Witten theory. So this is a major advance that was really only possible due to this physical reformulation and then using a lot of sophisticated ideas. Okay, so there's this thing, n equals 4, or sorry, d equals 4, Seiberg-Witten theory. It's some TQFT in 4 dimensions, and just like Donaldson theory, it's interesting mathematically and physically. And one thing I wanted to say, just to bring in, because another thing that I like to study, the superalgebra GL11 is going to make an appearance later on in this talk. And I just wanted to say a little bit that I got from this paper of Gukov, Putrov, and Vafa a few years ago. So I'm not sure how much of this is due to them and how much is just summarized by them in this paper, but this particular perspective on this Seiberg-Witten TQFT, at least I'm just summarizing what I read in their paper. And so if you consider a following 6 manifold, you take a 3 manifold M3 and then you cross with R, and then you cross with a certain 2-dimensional thing, this Seiberg-Witten curve, which is it's the surface inside C2. C2 is given this Taub-Nut metric, and you get this metric on the Seiberg-Witten curve. So you put all these things together, this gives you a 6 manifold, and then you can look at this thing called the 6-dimensional 2-0 superconformal field theory, or theory X, some people call this, on this 6 manifold. And one way to think about this theory is it comes from M theory. You can think of this 6 manifold as being an M5 brane in a particular 11-dimensional space-time. And so this perspective, okay, so you look at this 6D theory, you reduce on the Seiberg-Witten curve, so you get a 4D theory, and you do the twists in the right way, and you're supposed to get this 4-dimensional Seiberg-Witten theory from the last slide that's then related to, exotic 4 manifolds and that sort of thing. But one benefit of this perspective is it fits in with another thing that a lot of people are interested in, that's these categorified Chern-Simons invariants, such as Khovanov homology is probably the first instance of this stuff. But if you want to see those types of theories from this same perspective, all you're going to have to do, well, at least at this very non-detailed level, is replace this Seiberg-Witten curve with just 1/2 of it. Just take the W equals 0 half of it, but maybe stack it on itself n times if you really want U of n Chern-Simons theory categorified invariants. So Khovanov homology would, be related to certain 4- and 5-dimensional quantum field theories that come from this 6-dimensional setup where you have this long cigar, this W equals 0, but then you have, sort of multiple branes stacked on that. So, okay, but then I wanted to get to GL11, that's the point. And you can, so just like you could consider this W equals 0 cigar with certain number of positive branes stacked on it, you could also consider so-called anti-branes being stacked on it. And then this is related, although I'm not sure how worked out all of the details necessarily are, but it's at least should be related to supergroup Chern-Simons theory, U of NM, where it's sort of N bosonic variables and M fermionic variables. And now if I take
no, you shouldn't think of it like that.
Oh, I shouldn't think of it.
No, the GL1/1 is a single M fibrine on both of these curves. Right?
It is, the GL11 is it's sort of like a brane anti-brane on W equals 0, and then you do this sort of thing.
No, you don't want to do that.
I don't want to do that?
You don't want to do that. I know these pictures appeared in that paper, but you don't want to do that. In fact, the UL1/1 is a single M fibrine on the product of these curves. Go back a slide.
Yep. Mm-hmm.
It's a single M fibrine on ZW is equal to 0.
That's right. That's how they describe this. Okay,
that's
so you're
one
saying
single M fibrine on that. And if you want UN/M, then you want n copies on the Z is equal to 0.
Okay.
Basically, Z to the N is 0, and W to the M is 0. That's UN/M.
Okay, right. Yes, that's okay. So you're more or less saying that the connection between U of 1,1 and Seiberg-Witten theory is a bit closer than they suggest in this paper. They make
they're needlessly complicated. I'm not sure what they were doing there. But.
Okay, good. Well, that's good to know. Thanks. The comments like this are very useful for my understanding. I'm not a physics expert by any means, so this is very good. So
sorry, just to clarify. Sorry.
Yes.
So Mina, can you say what the n branes are on Z equals 0 and M copies of branes are on?
Firstly, they're no anti-branes at all. They're just M5 branes. Okay, so you can take one single M5 brane on the ZW is equal to 0 curve. Okay, that's reducible curve. So it's like one brane on Z is equal to 0 and one on W is equal to 0.
Okay.
That's GL1/1. And if you want GLN/M, right, then you'll take n branes on Z is equal to 0 and M on W is equal to 0, but they're all branes in all cases. They're not anti-branes. So it's as simple as that, yeah.
Okay, sure, got it. Thank you.
Okay, yes, that's good to know. Okay, so then maybe this picture comes from their paper, but is maybe not. Maybe it's a bit overcomplicated. But regardless, it should be true that the Seiberg-Witten theory should be closely related, possibly by the relation of identity, to categorified U of 1,1 Chern-Simons theory, all based on this Seiberg-Witten curve, sigma SW.
Exactly.
And so then mathematically, this sort of has been seen through relationships that usually mathematically one can make a lot of progress studying representation theory, GL11, quantum groups associated to that. These are sort of simple things to study when compared especially with gauge theory and hard analysis. And so a lot of the relationships sort of take this form, and that's going to be similar for what we're discussing in this talk. But we'd like more such relationships. This is sort of, we'd like a full mathematical understanding of what it means to categorify U of 1,1 Chern-Simons theory and why it gives exactly the same answer as the Seiberg-Witten thing. And especially the relationship between the topology and the algebra. Okay, so that's more or less the background on this 4D Seiberg-Witten theory that I wanted to talk about. But so this is some instance of a 4D TQFT. Some mathematicians might quibble and say it doesn't satisfy axioms. I'm going to talk about that right now, actually. So given a TQFT in this sense, some physical theory, then one thing you're supposed to be able to do is take a partition function on a 4 manifold that should give you a number. If I have a 3 manifold, I should be able to take some sort of Hilbert space of states that might arise as the cohomology of some operator acting on some larger space of states and these sort of things, but some sort of vector space level invariant. And in the most well-structured cases, there's a set of axioms written down by Atiyah that a TQFT is a certain type of functor from a category of cobordisms to a category of vector spaces. And in case you don't know what a cobordism is, here's the picture of that. You'll just have to sort of pretend, I'm talking about 4-dimensional cobordisms between 3 manifolds, but just pretend everything's 2 dimensions higher than it is. The cobordism is just a manifold with boundary, and it's sort of viewed as a morphism in some sense from one part of its boundary to the other part. You sort of split the boundary into 2 pieces, and you say, you make a category where the morphisms are these cobordisms. And then, I mean, if I have a cobordism, that's supposed to give me an evolution map so that if I have a state, the Hilbert space on one side, I'm supposed to be able to sort of generalization of time evolution, which would just be a plain cylinder, but it would depend on a length. In a topological quantum field theory, it can't depend on anything like length, but it can depend on the topology of the cobordism. So that's a sort of first, and this was very, the same year as Witten's paper, Atiyah wrote down this system of axioms trying to capture a first sense of what's going on with these TQFTs. And the most interesting examples, and this was acknowledged in Atiyah's paper, the most interesting examples don't satisfy these axioms. There's this B2 plus restriction so that it's not really topological on all 4 manifolds. The axioms aren't really satisfied. So that is, well, that's something to be aware of. But despite that, you can still say, well, what more structure could there be like this functorial cobordism structure? What more structure could be hiding in a TQFT? And oftentimes, even if the axioms don't hold, it's interesting to look down. We looked at 4 dimensions, that's sort of codimension 0 with respect to space-time. You can look at 3 dimensions, codimension 1, and assign a Hilbert space. You could go down to codimension 2. And then the right thing to assign is a category. And maybe in physics, from what I gather, the most familiar instance of this is if you're looking at a 2D conformal field theory, maybe describing propagations of strings in some background, and then, well, to a point, you'll want to assign some category of branes. And then for any 2 branes, then I can consider a Hilbert space of open string states where the endpoints are on those branes, maybe D branes or something like that. But that's an instance of a point is codimension 2 with respect to a two-dimensional world sheet. And so it gets assigned a category, derived category of brains sometimes. And you can keep going all the way down to a point in general. So a four-dimensional TQFT, every time I go down in dimension, I'm supposed to go up in category number. So for instance, in a 4D TQFT, I talked about 4 and 3 dimensions. If I go down to 2 dimensions, I'm supposed to get a category. If I go down then to 1 dimension, I'm supposed to get a 2 category. That's something that has objects, and then it has morphisms between those objects. Then it also has morphisms between the morphisms. And there's for those 2 morphisms, there's sort of 2 sorts of composition you can consider, and everything has to be coherent. This is a sort of technical subject that in modern terms is usually approached with homotopy theory. But in this talk, we're not doing details. This is just the idea. And then, so for a TQFT, if you looked at what it would want to assign to a point, it would be something like a 3 category where you have objects and then 1, 2, and 3 morphisms. So this is, if you can do this, if you can define a TQFT on all of these lower dimensional things, this tells you a lot about it. So there's this really inspirational result, in my opinion, by Lurie from about 10 years ago that says, if you satisfy a bunch of nice axioms that are phrased in this homotopical setting, and really you extend down to a point and you assign a fully dualizable object to a point, well, he's saying all TQFTs that satisfy these nice axioms would do that. And then anytime I have a fully dualizable object, I get a TQFT. So that really everything is determined by what's assigned to a point. I mean, this depends really heavily on.
Sorry, what is the statement about the fully dualizable?
Oh well, it's the invariant of a point in a fully extended TQFT is always a fully dualizable object of the target n category, but that's assuming a TQFT means XYZ axioms are satisfied, phrased with infinity n categories, and like it's too strict for something like Seiberg-Witten theory or Donaldson, but yeah, in this more constrained case that Larry's talking about, yeah, then it's always true for his type of TQFT. The invariant of a point is always it can be an arbitrary fully dualizable object of a symmetric monoidal infinity n category.
Sure.
Okay, I mean it's
I don't think I got it, but never mind. Maybe it's not.
Yeah, it's not necessarily, it's not really important for this talk. It's just the idea is just that if you have a TQFT that okay, wait, yeah, okay. So if you, sorry, I'm getting a little bit of lag. Okay, there we go. So if you can extend down, then that's good. That tells you more about how all of the things at higher dimensions should be structured and sort of glued together from smaller pieces. So extending down is some sort of locality thing. The more it extends down, the more local it is in some sense. That's one way I think about it. And then of course there's these difficulties. The axioms don't hold for Donaldson theory, Seiberg-Witten theory, even if you don't extend. If you do extend, then sort of, well, axioms, the extended axioms definitely don't hold. The theories sort of can't be defined on all manifolds of dimensions 4, for instance. But there's another issue, is that if you're trying to define invariance, say, of a 3 manifold, usually you need to pick some extra data. In the most sort of well-known cases, usually this is like maybe a base point in the manifold. And I'm going to particularly talk about a more elaborate type of extra data that, in Heegaard Floer, it's sort of, things are trending towards the most natural type of data to take is this sutured data. A sutured 3 manifold would get assigned an invariant, but not just a plain 3 manifold. So then it, but why a sutured 3 manifold? Well, that's because that's what Seiberg-Witten and Heegaard Floer theory tell us, but it doesn't seem that necessarily every TQFT should be, sometimes it's taken to be, this is sometimes taken to be a sign that the usual TQFT framework, maybe it's just not good enough, or it's just not the right thing for these things like Seiberg-Witten theory. that maybe you need a more geometrical type sutured TQFT or something like this. And this is a valid point of view, and it's very interesting to think about these things. I want to propose a different point of view here, which says that more or less, for this Seiberg-Witten theory, it is more or less close to right in terms of what should get assigned, what should get assigned invariants and what those invariants should be. So that in particular, if you're going to say things are assigned to sutured manifolds, you're really going to think of a sutured manifold as some morphism in a 0, 1, 2, 3 cobordism category. That's what I propose thinking of this sutured structure as being. And we'll talk about this more for sutured 2 manifolds than 3 manifolds. 3 is similar, but a bit more complicated. But I'm proposing that even though it's known that we're not going to be able to get a fully extended TQFT satisfying all of Floer's axioms for Seiberg-Witten theory, that it's still possible that we should be assigning things to some, if not all, morphisms, not all, but at least some morphisms in these higher cobordism categories, that's the right sort of thing, and that we should be assigning them not anything especially weird, you know? Categories, 2 categories, 3 categories, more or less, appropriately interpreted. And so this involves more or less a reformulation of how some things in Heegaard Floer are typically thought of. But if you take this reformulation, then it becomes more evident that the fundamental thing you should be looking at is not the invariant of a circle, as is often considered, but rather the invariant of a point in line with sort of the most optimistic hopes about extending down. You always want to get to a point. That's the holy grail of extending a TQFT, is defining something for a point. Maybe it won't allow you to rebuild everything, but at least it's the lowest level of extension you can get to. Okay, so there's a preliminary guess that comes out of this work with Raphael, and this is most naturally explained in terms of Heegaard Floer homology. So we've been talking about this Seiberg-Witten TQFT, but what I think about mathematically is this thing called Heegaard Floer homology, which is more or less an approach to the Seiberg-Witten TQFT. It's always based on looking one dimension lower than you actually say you are. So let me say a little bit about that, unless there's any questions at this point, and we're going to this Heegaard Floer section.
I think we'll have more questions when things get more concrete. It's a little bit. I'm not
Yes.
sure I followed all of this, but let's actually get to the Heegaard Floer story.
Great. Yes. Good. Okay. So, well, first, it's informative to look at the Donaldson story, where there's this conjecture, the Atiyah-Floer conjecture. It's a difficult thing in analysis that still hasn't been proved, but I mean, the ideas behind it are well thought out. And that's saying, well, what does this Donaldson TQFT, this Donaldson-Floer thing, what does it assign to a surface? And the conjecture is it's some Fukaya category. I'll say epsilon and what that is in a second, applied to a certain moduli space. A moduli space of, well, you can think of it as R invariant instanton solutions on, R2 invariant instanton solutions on R2 times F. Or I can think of it as like R invariant flat connections on R times F, or I can think of it as flat connections on F, because somehow the 3 manifold, I sort of didn't explain on the slides, but the 3 manifold invariant, the Hilbert space of this TQFT on a 3 manifold is some chain complex whose generators are flat connections on M3 and SU2 connections if you're looking at this SU2 Donaldson theory. And so this Atiyah-Floer conjecture says, well, you should go down to surfaces. And for a surface, you should assign this thing called the Fukaya category, as objects are Lagrangian submanifolds of that moduli space of flat connections on the surface. Okay, so if I have a flat connection on the surface F, I can ask if it extends on, now say I have a 3 manifold M that's glued together along F from 2 pieces, M1 and M2 with boundary F. Okay, then if I have a flat connection on F, I can ask if it extends on M1 and M2, and the ones that extend on M1 give some Lagrangian submanifold of this moduli space. The same for M2, and so each of those give an object of the Fukaya category, and I can take morphism complex between them. Oops. And that the conjecture is that is the homology of that morphism complex is the Hilbert space of this theory. So that this is conjecturally one way to build the Hilbert space of this Donaldson-Floer TQFT is for a manifold M, you can view it as being glued from two pieces. And then you have this Lagrangian Floer group that comes up. That's a morphism space in the Fukaya category. And that this homology group is the, in this case, the instanton Floer homology of the manifold, the Hilbert space of this theory. And then the epsilon about what is this Lagrangian Floer group? Well, you have this moduli space, say, of flat connections on F. This is a symplectic manifold, and I have two Lagrangians inside. And to that data, I'm associating more or less, well, Floer is associating a chain complex whose generators are intersection points between those Lagrangians and whose differential counts pseudo-holomorphic curves in some sense. And so in this case, an intersection between the Lagrangian on one side is the connections that extend over M1. And then if I take an intersection point with the other side, that's a connection that also extends over M2. So the generators of this Lagrangian Floer complex in this case would be then flat connections on M, just like for the instanton complex. And then
are we trying to explain the relation between Seiberg-Witten theory and Heegaard Floer homology?
Well, yeah, trying to motivate why you would do the following thing for Seiberg-Witten theory. Well, after a discussion of Heegaard splittings, why you would take and make the following definitions and hope that that recovers Seiberg-Witten theory.
Okay, go ahead.
Okay.
Sorry, can I ask one question? So what does the flat connection, the modular space of flat connection of SU2 bundle over a surface look like? Is that compact or is that smooth or?
No, I think
kind of
it's
structure
bad in general, but I'm not an expert on that stuff.
I mean, I thought the explanation of relation to Heegaard Floer homology is it goes not by flat connections. For example, if you took your surface to be R2 or S2, there'd be no flat connections.
That's
I thought what you want to do is you want to study Seiberg-Witten theory the way Taubes does. So basically introducing these perturbations where you end up studying the theory becomes equivalent to studying in your context where the three manifold splits along F to studying moduli space of vortices on F.
Yes, that's right.
And then
exactly.
the connection to Heegaard Floer. In fact, I think that's how Taub proved, right?
Yeah, exactly. Yeah, but
that thing makes sense. That thing makes sense, I think, physically.
Yeah. But before right, those ideas first came about in trying to study Donaldson theory, right? And then they were applied to Seiberg-Witten theory. So that's just the order I'm trying to. Maybe I'm taking a slightly long-winded approach, but yes, that's a couple of slides from now. So this is this conjecture in Donaldson theory, and here's one way to think about it. Say I didn't know how to define the Hilbert spaces. Well, then I could pick a particularly nice splitting of a given three manifold and try to use this conjecture to define Hilbert spaces. And there's this type of splitting that comes up especially in Heegaard Floer homology called a Heegaard splitting due to Heegaard. And it's basically a decomposition of a three manifold as two handle bodies of genus G glued together along a surface. A handle body is just a solid genus G surface. So I learned this from a physicist back in grad school, so I couldn't resist trying what he called the bagel-bagel decomposition of S3. This is a Heegaard decomposition of S3. And you have one genus one handle body, and then the complement in S3 is also a genus one handle body. So this is S3 being glued together, out of two handle bodies glued along their common boundary surface. And you can always pick one of these for a three manifold. Here's another one for S3. This one is a genus 2 Heegaard splitting because this thing I drew is a genus 2 handle body and the complement is also a genus 2 handle body. So you could do the following thing. You're given your M3, you're going to pick a Heegaard splitting, any one, and then you're going to say, okay, look at the moduli space on the surface, look at the Lagrangian of things that extend on one handle body, Lagrangian on the other handle body, take the Lagrangian Floer complex, and take its homology. And then you're going to try to show that this thing is up to isomorphism independent of the Heegaard splitting. And if you can do that, you've defined something that, at least conjecturally, should recover this Hilbert space of the theory. Okay, so this was ideas that had been discussed and are quite difficult in Donaldson theory, but in Seiberg-Witten theory, it's kind of backwards. Seiberg-Witten theory came about in '94, but it wasn't really until almost 15 years later that Chern-Simons' book appeared that rigorously constructs from gauge theory the Hilbert spaces of 4D Seiberg-Witten theory on a 3-manifold. So before that was really written down and published, one could try to take this alternate approach and see if you can get something more tractable anyway. You could say, how about this idea, exactly like you're saying, you're going to look at Seiberg-Witten equations on R2 times your surface that are R2 invariant, and let's go to reduced vortex equations, and you're going to play the same game. Instead of saying flat connection moduli space, I'm going to say vortex moduli space everywhere. But I'm just going to hope that the same machine defines me something and that I can prove that at the end that it's independent of Heegaard splitting. And that's what Ojva-Szabo did, and that's the theory of Heegaard Floer homology. So here's the vortices. So if I look at these, rather if I'm looking at Seiberg-Witten equations rather than Donaldson equations, then then it's going to reduce not to flat connections, but to these vortex equations. The moduli space of those is known to be, well, they're labeled by vortex number, and the vortex number can be some non-negative integer, and corresponding to that non-negative integer, you have a symmetric product of your surface. So as k gets bigger, this is a higher dimensional manifold. It's like f times dot 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 times f mod the action of the symmetric group. It's like a collection of k unordered points in f, possibly allowing collisions. Those are fine. So that's the moduli. That's the vortex moduli space on your surface. It's this disjoint union of symmetric powers. So now what you're going to do in this theory is you're going to pick some diagrammatic representation of a Heegaard splitting, okay? And that's actually going to work out really well. You're going to pick this thing. It's easiest to just put the picture and then say the text. This is a Heegaard diagram for S3. I draw the same surface of the bagel I had before, this 2-hold bagel, okay? This is just genus 2 surface. But then I'm going to draw a pattern of red circles and blue circles. Red ones are disjoint from each other. Blue ones are disjoint from, and the number of circles of each color is the same as the genus of the surface, 2 in this case. So this is supposed to represent the whole S3, the manifold, together with its splitting along the genus 2 surface. And how you see that is, well, from this diagram, I can rebuild the S3 as follows. I glue in like inside this surface, along those blue circles, I'm going to glue in discs, and then I cap that off with the ball. That'll build this sort of interior bagel. And then outside, I can think of sort of capping off those holes with pancakes, more or less, and then cap off the whole thing with another ball. That builds the outside bagel. So there's a well-defined procedure for doing this, and so in this sense, a Heegaard diagram always represents some 3-manifold. And so you're going to, when doing this Heegaard Floer thing, you're going to pick a Heegaard diagram representing your 3-manifold, and then you notice the following thing. Inside the G-fold symmetric product of sigma G, there's a natural, well, you have 2 natural Lagrangians. If I take the first red circle times the second red circle, mod sigma 2, that's some Lagrangian. I take same with the blue circles, that's also some Lagrangian. And the sort of key the claim here, the key ansatz, is that these are the right ones for Seiberg-Witten theory. These are the points in the vortex moduli space that extend over M1 and M2 in the appropriate sense. These are exactly your ones that you would get from a Heegaard diagram representation of your splitting. Okay, so if you believe that, then you can more or less do simple computations that have nice pictorial meaning in terms of the Heegaard diagram itself. So like this little blue region that I drew is a domain for some holomorphic curve in the sense of Heegaard Floer homology. But the nice thing is that you have these patterns. Like this domain I know always contributes. I don't have to think about complex geometry. If I see a bigone like that, I just know in Heegaard Floer homology that always counts. So in many cases, you can take what would be a difficult analytic problem about moduli spaces of solutions and just be like, yeah, but I see this type of picture and this type of picture and this type of picture. There's a theorem that says all of these count. And then given that data, plus the fact that I have like d squared equals 0 or something, you hope you can really deduce everything else you need. And that is more or less the Heegaard Floer game that I play, at least. So that is, and and the reason I'm presenting it this way is for a reason related to this project, but I'm really wanting to present Heegaard Floer homology as being based on an ansatz about what's assigned to a surface. It's saying, let's guess that a surface gets assigned this Fukaya category of symmetric products. And then based on that guess, plus a few more compatible guesses, then you can define something for three manifolds. Now, this has now been shown, like you said, Taubes and others have shown that this idea does recover Kronheimer and Rouquier's definitions of Seiberg-Witten theory for three manifolds done gauge theoretically. So this ansatz is at least, confirmed for three manifolds in that sense. And that's all well and good, but you could keep trying to go down. That this just sort of deals with Heegaard Floer homology for three-dimensional manifolds, like the Hilbert space on M3. But what if I want to go down to, we said we made a guess about a category for a surface, but then we only used it for Heegaard splittings. What about more general splittings?
Before we go on,
yes.
can we just review, just recap the translation between objects in Heegaard Floer theory and Seiberg-Witten theory? So, for example, the Lagrangian branes, the intersections between them, what is their meaning from gauge theory perspective?
So there's, okay, and here, I don't know the right name of the equation. Well, there's like the 3D Seiberg-Witten equation. I think in general terms, it's like if I look at the Seiberg-Witten equations on like a three manifold times R and require them to be R invariant, I can look at solutions to such equations on a three manifold with boundary, limiting to some vortex solution on F. Those, the solutions that extend from a vortex solution on F to some solution on all of, say, handle body H1 on one side, the red handle body, that the claim is that this is, given this diagrammatic representative, it can be viewed as this product of red circles inside the symmetric product.
So a choice of a Lagrangian is a choice of solutions of Seiberg-Witten. It's on a filling of a three of F, right? Your surface.
Yep. Yep. It's right. It's a choice of, yeah.
So the brain on the okay, good. And then humps between branes, the intersections between branes.
They're intersections, right? So that's like a solution that extends out to all of.
To understand both. Okay. And you view this as perturbative solutions, so we still have to correct them with some differential and so forth?
Yeah, there's a differential that, right. So in the Chern-Simons setting, that would be counting monopole solutions on a four manifold, and then the sort of Atiyah-Floer style conjecture says, well, that should be the same as this Fukaya stuff, this pseudo-holomorphic curves in your symplectic manifold.
And this map between the action of the differential in Seiberg-Witten theory and the action of the differential in Heegaard Floer theory has, I guess that's part of the theorems that Taubes must have proved, right? Okay.
Exactly.
That is the same thing. Okay, great. Thank you.
Great, no problem. Okay, so what happens then if you try to look at more general splitting, and I'm going to phrase it that way, but and call this bordered Heegaard Floer homology done by Lipschitz, or initiated by Lipschitz, and Thurston. But I really want to emphasize what this doesn't do is say, okay, now we know what to assign to a surface. Now we're just going to generalize to allow more general stuff, not just a handle body on each side. Rather, it's going to do the following thing. And this is, in some sense, why Heegaard Floer homology is always about going one dimension down. It's going to introduce a new cut to your three manifold transverse to that Heegaard surface cut that you already had. So you're still going to be thinking about a three manifold cut into two handle bodies. But now I'm going to introduce yet another cut, and now this one can be arbitrary, decomposing it into any two three manifolds. And I'm going to try to forget I had the Heegaard, just like in the definitions of Heegaard Floer homology, at the end of it, I think of it as a three manifold invariant and forget the decomposition. Similarly here, I'm going to try to analyze things just in terms of I'm going to view things just in terms of the new cut, but actually when I work with them, it'll be in terms of the additional Heegaard surface cut, okay? And a picture for this looks like this. So we have this Heegaard surface with the red and blue curves. This is a different one, this Heegaard diagram. And then I can imagine there's, there's some like top handle body and bottom handle body, and I sort of glue them together in green, and that gives a closed 3 manifold. But now I'm going to make this additional orange cut, and I'm going to cut the closed 3 manifold along a surface, and that surface, well, in general, it could intersect if it intersects Heegaard surface transversely, it'll be in some collection of circles. I'm going to assume for now it's a single circle, and that it only intersects alpha curves in the Heegaard surface. If you make this new cut, then I can try to understand, I want to understand like the orange cut surface, and then the left and right halves, everything in terms of that black Heegaard surface in the middle. Okay, so the orange surface F, I want to understand that in terms of that bold orange circle that I drew, F intersect sigma, something related to a circle. And I'll be more precise in just a second, but that'll get assigned, something related to a circle will get assigned a DG algebra. And then you can take a category of modules, and that in some sense will be a category assigned to your surface. And then if I look at the left and right pieces here, I want to understand those in terms of the left and right halves of this Heegaard diagram, right? So for the green thing, it's a 3 manifold being split along a surface. But if I just look in terms of the Heegaard diagram, it's a surface being split along a 1 manifold. I want to understand my left and right 3 manifold pieces in terms of their sort of partial Heegaard diagrams, these 2 halves of these cut up Heegaard diagrams. So this is the philosophy behind bordered. And they get assigned A infinity modules over the algebra of that circle. And well, the algebra associated to the surface, which is represented by a circle-like diagram. And from this, you can recover like Heegaard Floer for closed 3 manifolds by any, you pick any sort of decomposition, not necessarily into handle bodies, but any sort of decomposition can be studied in these terms, but you always have this additional handle body decomposition in mind as well. Okay, so that's a sketch picture of what's going on in bordered. And so just like for ordinary Heegaard Floer, you could think, okay, that's doing Seiberg-Witten theory based on an ansatz about what gets assigned to a surface. And so here, since we introduced a transverse cut, but we kept that sort of extra one that we had, we can similarly ask if, well, can we think of bordered Floer homology as being based on some sort of ansatz about what's assigned to a circle by Seiberg-Witten theory? And this is a question that a lot of people like to ask, what's assigned to a circle? And well, things get a little bit muddy. And the first thing is that I've been lying about the data required for Heegaard Floer homology. You would need at least the following thing, or a more elaborate version of it. You need a base point in your manifold, and you're going to take that from coming from a base point in your Heegaard surface. And then when you do this additional bordered cut, you're furthermore going to assume that the base point lies on this bold circle where it's both on the Heegaard surface and on your cutting surface F, okay? So that this bold circle that we were looking at in terms of representing the surface F to define an invariant, well, it's really a circle with base point. Okay, and now I can be a bit more precise. If I look on the left side of this Heegaard diagram, for instance.
Can I just ask a question?
Yes.
So, I mean, in principle, your orange surface that's cutting the 3 manifold into 2 other halves can be something very complicated. Yes. At the same time, in terms of what the Heegaard surface F is going to see is, I mean, at best, you have the freedom of chopping up the Riemann surface into, smaller pants or what have you, right?
Yep.
Do you see some additional data arising here?
Yep,
in terms of
exactly.
What the orange surface
the matching pattern of the red arcs that you're cutting through. So it's not just this circle with the base point, but you also record, if I look at I just look at the left side of this Heegaard surface, I see this orange bold circle intersects a red arc that then goes around and matches up to some other point on the orange circle. And then similarly, maybe it's easiest actually to just go to the picture of this. So if I look at this picture, the leftmost thing I just drew that orange circle and then the red arcs in the left Heegaard surface that end on that circle. Okay, and I can redraw this picture like this, but it's a circle with the base point and then this matching data. So that's what the Heegaard surface remembers about your surface. Well, really your diagrammatic representation of the surface with respect to this Heegaard diagram for the 3-manifold. But it's remembering where that surface, basically where that surface intersected those two handles. That in the first example, the pancakes that you glued on for the red circles on top of this bagel, those in general, okay, there's going to be some of those going across the boundary, and it's going to be cut. They're going to be cut by this orange surface F, and F is going to remember these arcs. Let's maybe go back. So if I think like that outer red circle, just think I have like a dome over that outer red circle. But now when I cut with the orange surface, it's going to cut that dome through an arc. And that arc will be, well, it'll be in the orange surface with endpoints on the orange circle. That's all I'll say.
Okay. So from the perspective of Heegaard Floer theory, if you think of it as an A model or a Fukaya category,
Yep.
Then what we are using here is that we can get Fukaya categories on surfaces by sort of gluing Fukaya categories on pants, right? And you're now lifting that structure to Seiberg-Witten theory.
I would say that's actually the next thing down. This is saying I can get the this bordered is about getting the Hilbert space on M3 from the Fukaya category on your surface. And so if I do want to go the next level down and look at one dimension, and actually look at one dimension, then yeah, it's something about gluing along a circle and recovering. But I think that's probably, in my view, best thought about in like the next few slides on this cornered business, because we are yet again going to make another cut, and we're going to then reinterpret all of this stuff. Okay. So maybe that's not the best answer, but
sorry, can I ask one question?
Yeah.
So this F and sigma, one should view them like democratically, like there's no real difference. They're just some separating hypersurface.
In some sense, yes. You know, in some sense, if you, what I'm going to propose at the end is that, yes, there should be some theory that assigns something to a point and assigns something to any surface, and then you should be able to build up. And in that theory, these things should be viewed democratically. But like, you know, in search of democracy, sometimes some compromises need to be made. And so as currently formulated, the theory doesn't necessarily treat these democratically.
Okay, you're saying the Heegaard Floer is like this first cut, and then you further make a cut based on this.
Yeah, the Heegaard surface is like a second-class citizen. It's like always used to help out your understanding of one dimension up. And so it's secretly using how it works at one dimension down. But then you say, oh, but this is, no, we're just doing bordered, which is decomposing a 3-manifold along a surface. But secretly, the work is being done by the unappreciated Heegaard surface, not to be too political.
Okay, and just to make sure I understand the terminology, the Heegaard Floer theory, the ambient space is what? Is that surface sigma, or is that symmetric power of the sigma?
What do you mean the ambient space? Like that you're taking
the Heegaard Floer theory, it's like some Lagrangian Floer theory.
Oh yeah, in which symplectic manifold, it's the symmetric product. Yeah, in this case, sim G of sigma G.
Okay, and you're saying like even though that's the one is doing things in that high power of sigma G, the disk one can visualize them as lying on the surface itself.
Yeah, so if you're working if you're working in sim K of sigma, a point in that can still be just visualized as an unordered collection of K points in sigma. And like a path in sim K of sigma can be visualized
simultaneously.
K, yeah, exactly. Yep. And so your holomorphic curve bygone things are going to look like more complicated domains, possibly with a bunch of red and blue segments of their boundary when you draw them in sigma itself, but still it's relatively manageable to visualize this sort of thing as compared with other sort of formulations.
Okay, sure. Thank you.
And you're saying that you have to place the base point on the cutting circle?
Yep, or at least that's how they do it. I want to propose a way of thinking about this that's not based on base points, but rather sutured structures, and we'll say a bit about that. But yes, this is how the LOT style formulation of bordered Floer works, is that base point must always be on the cutting circle. Okay, any other questions? Okay. So, right. So this is the data then they use. This is what that circle sort of sees. It sees just some endpoints of red arcs, but those, each comes matched with a pair, matched with a partner. And so you can, just like there's a way of recovering the three manifold by handle gluing from a Heegaard diagram, there's a way of recovering the surface by handle gluing onto this pointed match circle. So what LOT are going to do is they're going to say, okay, well, what are we going to assign to a surface? We're going to pick a pointed match circle representative of that surface. We're going to assign some DG algebra, and then an appropriate derived category of modules over that algebra is not going to depend on the pointed match circle we picked for the surface. That is the standard story. But then you can think, okay, based on our earlier philosophy, now it's not about, we're not really working with what Seiberg-Witten theory assigns to a circle, but rather a pointed circle, right? And that's less in the spirit of this Jacob-Floer TQFT stuff. As you see circles more often than pointed circles there. So what I want to propose is, well, let's look at the sutured version, which looks worse at first, but then it can be made better. So there's this thing called a sutured three manifold defined by Gabay in 1983. And first used for sort of hardcore low dimensional topology. And
sorry, before you go on, from a Seiberg-Witten perspective, the need for this extra base point is what?
Well, I don't know. That's a good question. That's probably like Kronheimer Mrvka could explain that very well, but I haven't studied the gauge theoretic side.
Okay.
From the Heegaard Floer perspective, I mean, it gives, you can define things, but in many cases, they're either trivial or not well defined. If you don't, I mean, you can define chain complexes where you allow curves to go everywhere and you don't take the base point into consideration. Often those are not chain complexes. Often d squared is not 0, but sometimes you can still, you don't want to get d squared equals 1, right? With the most naive version of the theory, you get a chain complex quotes, but it would have like d squared equals some scalar, but not, you can deal with that by like doing deformations or whatever and having d squared equals some polynomial thing. That's very much what's done in Heegaard Floer. But from that side, I don't know the gauge theoretic side, but from the sort of Heegaard diagrams and what we do with it, then it's just like the specific constructions don't really give you. So that's a kind of unsatisfying answer. Gauge theoretic answer would be better. Okay. So there's this thing called sutured manifolds, and they're compact three manifolds with boundary. And then you put extra structure on the boundary. And Gabay is very careful because he needs these for certain theorems about taut foliations. But for the sutured Floer homology business, you can get by with a simpler sort of way. Do I even say, okay, yeah, here's a sutured, I'll go back to the other side, but a sutured three manifold is going to be a compact M3 with boundary oriented. And then its boundary is just going to be divided into two regions by a one manifold, compact one manifold that you call gamma. So here's just my example of this. I take the three-dimensional ball, and then I just draw some one manifold that divides up, and then I pick, one region is R plus and the rest of it is R minus. So this is a sutured B3, so a sutured structure on the three-dimensional ball. So relatively soon after the definitions of Heegaard Floer homology, András Juhász, well, he generalized Heegaard Floer to this setting, which is actually really neat because it's a joint generalization of Heegaard Floer for three manifolds and for knots. And how does that work? If you say I take a closed M3, okay, and I say it has some base point, well then if I cut out a neighborhood of that base point, an open neighborhood, I'll get some three manifold with S2 boundary, and on that S2 I'm going to put a single suture equatorial suture, and I'll have an R plus disk and an R minus disk. And this is sort of a map from closed three manifolds with base point to sutured manifolds. And then UHAS defines Heegaard Floer for sutured manifolds. And if it's one of these that came from a closed M3, then the sutured Floer of this is the same as the original HF hat of the M3. So then in that sense, the sutured Floer
Can you repeat the statement again? Because I'm not familiar with a suture structure. So.
Okay, yep, that's okay. So if I take a closed M3 and then cut out an open neighborhood of a point so that I just get a three manifold with S2 boundary, and I put this sutured structure on it.
So the suture structure is extra, right?
Yeah, in some sense, it's like extra data. It's like a decoration on the boundary of this manifold.
Okay.
And I pick, I make this sure there's many more general things that don't come from this construction, many other sutured manifolds, but these are some sort of sutured manifolds that I just got from closed three manifolds with base point. And then UHAS defines Heegaard Floer for sutured three manifolds in relatively large generality. But if you apply it to these ones that you got from a closed three manifold, then you just recovered the original HF hat of the closed three manifold.
And you're saying it has a natural generalization to including knots.
Yes, exactly. So that is, so now if I take closed M3, but it has a knot in it, now if I cut out an open neighborhood of the knot instead, this will give me some manifold with T2 boundary, and I'm going to put meridional sutures that sort of link the knot in the standard way. And then, I mean, it's sort of symmetric which region you call R plus and R minus, but you put two meridional sutures. This gives you a sutured three manifold. And again, the sutured Floer homology of this type of sutured three manifold recovers HFK hat of your original knot in M3. So this is, from this point of view, this already makes me like the theory because, it puts the three manifold and knot theories on an equal footing. And I'm saying HF hat, but there's work extending this and saying things in the minus setting. It's most natural maybe in the hat setting, but it also should be, in my view, the right way to view all flavors of Heegaard Floer as applied to sutured three manifolds. So
and in the original setting of Heegaard Floer, you don't view the knots and three manifolds as put on the same footing?
Right, you view that as HFK, and that comes from this deformation of the HF complex of the underlying three manifold. And I get, you could think of they're on the same footing as that your closed three manifold is always like, your closed three manifold invariant is always just the same as HFK of the unknot, but that's not quite as nice as what's going on here, is where the three manifold construction and the knot construction are both two equally sort of, and then a whole bunch of other variants of the HFK construction also make sense. It's just applied to different sutured manifolds.
Sorry, maybe I'm not understanding. Maybe my familiarity with Heegaard Floer stories is a little shaky. So I mean, in Chern-Simons theory, if we were to study GL1/1 Chern-Simons, and I thought that this is in the end supposed to be a story about that, studying three manifolds and studying three manifolds with knots it's one single story. So I understand. Is it not the case here that I can ask a question of studying three manifold itself, or I can just insert a knot? Doesn't that sort of naturally fit into one and the same?
Yeah, I mean, from that point of view, I can insert a knot, or I cannot insert a knot. Well, here's another way to say it, is that this sutured perspective is really not based on the knot so much as the knot complement. Like, you're really cutting out the knot and assigning something to the complement. And it's a theory in which the knot invariants are like that. And the three manifold invariants, it's not saying that, it's just slightly different. And that's sort of the theme of this talk, is that things are a little bit, I'm proposing just a different way of viewing things that seems most appropriate for Heegaard Floer based on this recent work. But rather than viewing the closed three manifold invariant as I didn't cut out any knot complement at all, you're going to view it as, instead I cut out a small ball and put a suture on it.
Okay, thanks.
Yep, no problem. But yeah, I agree that in both theories, yeah, the closed thing is more or less if you don't have a knot, but it's subject to this one difference here. Sort of, it's a little bit, well.
So one question.
Mhm.
Yeah, sorry. About the knot, the picture, the suture
Yep.
doesn't separate the boundary, does it?
The sutures should separate the boundary into R plus and R minus regions, and that I'm drawing one of those as shaded and one of them is not shaded.
The boundary is a T2 and you're just suture on a circle or on
There's two sutures.
Okay, two sutures.
Yeah,
okay,
sorry.
sure.
It's like I didn't draw the little back part going across back, but it's like two circles, and then if I cut out both of those,
Sure.
then I get, yep. Okay.
Yeah, okay. Thanks.
Yep, no problem. Okay, so then you can not stop at three manifolds, but you can say, what happens if I cut up a sutured three manifold along some surface? And if I, say I look at this picture and I just cut, say, along the equator, and I assume that things intersected the equator transversely, which wasn't quite the case here. But if I cut along a generic circle here, then what I'm going to get is, and I'm cutting this solid ball, remember? So then I would get like a disk, and on the boundary of that disk, I would remember some suture data that came from the boundary of this original ball. So we're going to consider, okay, sutured surfaces. Sutured surfaces are what you would get by cutting a sutured three manifold. And it's a compact surface F with boundary, and then the boundary of the surface is decomposed into two regions. We'll call them S plus and S minus instead of R plus and R minus. And then we'll call, they interface along what's now going to be a zero manifold, a finite set of points, lambda. So that's the sort of surface you get from cutting up a sutured three manifold. Here's an example of this sort of thing. This is just a T2, but then I cut out a small disk, a small neighborhood of a point. And I put, so this I sort of got from a closed surface with base point, just by a two-dimensional version of that previous construction I just said. So this is the sort of thing that, so just like Juhas goes and reformulates standard Heegaard Floer in this sutured language, Zarev went and did the same thing for bordered Floer homology. And so this means we're not going to be working with pointed match circles anymore. We're going to be working with a different type of thing. So let me, to introduce this, let me just say, if I took a sutured three manifold and I picked a Heegaard decomposition, somehow Heegaard decompositions, Heegaard diagrams for sutured three manifolds are even more natural than the standard case. You just sort of allow Heegaard diagrams with boundary, and you treat the boundary in the right way when building the manifold. And it's very natural to represent a sutured three manifold with a Heegaard diagram. And now if I cut that Heegaard diagram, rather than seeing a pointed match circle now, instead what I'll see is one of these arc diagrams. So, I mean, and I'm not going to require I'm cutting along a single circle anymore. I might cut, and this would be easier with the picture, but it's maybe not the most important thing for this talk that this is entirely visualized right now of like why this is what you get when you cut your Heegaard diagram for a sutured three manifold. But like I'm taking like a Heegaard diagram with boundary for a sutured three manifold. Say like a disk, and maybe I have some like tubes and stuff on each side, and there's some blue curves and some red curves. They don't touch the boundary, but then some red curves run through the middle, and then I'm cutting my surface, but maybe there's also a tube, okay, that stretches from one side to the other. Okay, here's how to explain it. So now I'm going to cut this whole thing right down the middle, and that cut is going to go through this tube and an arc on the Heegaard surface. And on the tube and the arc, I'm going to possibly have red circles that got cut through by this cut. And I'm going to record their matching pattern. That's what this arc diagram is. So everything is just what you would get if you started with sutured three manifolds instead of closed ones with base point. And this is just a picture of if I have one of these diagrams, how do I build the sutured surface with handle addition? There's sort of a standard way of doing this. So in Zarev's version of the theory, it's not that a pointed match circle gets assigned this algebra A of Z and then a category for the surface. It's that this arc diagram, and sometimes I call these chord diagrams that I learned from Bob Penner because they're studied sort of in his field of topology as well. But these arc, I'll call them arc diagrams here. These things, well, they're the replacement for pointed match circles in this bordered sutured theory. And a major theme of this talk, I guess, is that we prefer arc diagrams over pointed match circles. But one thing to point out is that if I look at the interval components of the arc diagram, those are in bijection with the interval components of the S plus part. I guess this isn't so important for maybe just remember that by this construction that I didn't say too explicitly, interval components of the diagram, like that orange interval here, are going to correspond exactly to your interval components of the S plus part of the boundary of the corresponding sutured surface. And similarly for orange circles, those will correspond to orange, or they'll correspond to S plus components of the boundary of F. Okay, that'll come up in just a second.
So somehow the whole surface is encoded in the single arc diagram. The whole
Exactly.
surface plus its boundary.
Yep.
Okay.
Yep, exactly. There's a very sort of efficient way to, I mean, this procedure, I mean, this picture is, for me, like, tells the whole story. You just thicken your intervals and circles of your arc diagram so that they become these little surfaces. And if it was a circle, then it's like one side is orange and that's S plus, and the other side is black and that's S minus. If it's an interval, it's like you put those two green points and then one side is orange and one side is black. And then you just do the handle additions on the black side. And that's how this thing works. And it's a theorem that I think the precise statement is that any sutured surface such that every connected component of the surface has at least on its boundary some intersection with S plus and some S plus parts of its boundary and some S minus, then it can always be represented by an arc diagram. And there's a way to, if two arc diagrams represent the same surface, then they can be related by a finite sequence of these arc slide moves. So it's a nice, and that's why these low dimensional topologists like it too. It's a nice combinatorial way of representing surfaces. Okay, so
sorry, just maybe one comment. This really looks like you have a surface and you have some stop on the boundary of the surface and you're doing some skeleton.
Exactly. Well, that'll come up in just a second. Right here, we start to see the word stop. But yes. So I just wanted to say, so just like Juhas does for the ordinary things, you can say that Zarev generalizes what LOT does as follows. So LOT start with this pointed match circle on the left, and they view it, if you go down, as representing this surface with base point. Okay. But Zarev's is going to say, okay, the surface with base point, we're going to cut open, like we said, and add these. We're going to cut out a neighborhood of the base point and add these sutures. And then for the pointed match circle, you're going to do a similar thing in order to represent that sutured surface in the bottom, right? I'm going to, if I'm given a pointed match circle, what I'm supposed to do is actually cut that open at the base point and have an interval. And then that interval, that matched interval, will be an arc diagram that represents the corresponding sutured surface. And then it's true that if I just look at the top edge of this diagram, well, Zarev's going to assign A of Z to an arc diagram, but if the arc diagram comes from cutting open a pointed match circle, then it's going to agree with LOT's original algebra for the pointed match circle. So in that sense, Zarev is generalizing LOT's algebras here. And then similarly, he generalizes LOT's three-manifold invariance, although I didn't try to draw pictures for that this talk because I want to get to sort of the part of this talk that's most related to my work with Raphael. But this, I just wanted to indicate how Zarev and LOT are related.
And you would, I see, and somehow you'd always divide a circle into only two components, right? I guess for the why are we dividing it into two components?
And this bottom
yeah.
edge of the square, that's analogous to, you could definitely consider sutured structures on a surface where you're dividing a circle into many more components, and Zarev can define things, and there's arc diagrams representing that. But if you want to recover what LOT do, it's always just going to be this type of arc diagram representing a sutured surface. That's just this very simple type of thing. Just like in the three manifold setting, if I'm going to look at HF hat for closed three manifolds, that's always interpreted in terms of a very simple type of sutured three manifold. It just has a single ball as boundary and a single equatorial suture. This is the analogy here.
Okay.
Okay. And then yes, it's true, this sutured structure gives you exactly what you need to define a partially wrapped Fukaya category of the symmetric product for various k of this surface. Because when you're doing this wrapping, you're going to, well, if I look at, say I look at this picture on the right, with this torus with two holes cut out of it, that's what it's supposed to be. And then I have these red arcs. Well, I could treat, in this case, it's sort of genus one. So I could just treat, I could look at sim one, and that's very natural. And then those arcs are Lagrangians. And I could do a partially wrapped Fukaya category of these things, but how am I supposed to wrap? Well, if it's orange, I just keep wrapping forever. But if I hit a black region of the boundary, I stop. And so that's, in some sense, the suture data is the right setting for the general statement of a result of a RU that says basically these strands algebras are recovering what you had hoped they would recover. You had hoped, to get something that's in the end going to be related to the two-dimensional content of the theory when doing this, which is like Fukaya categories of SimKF, and their result is saying that these explicit bordered algebras of LOT and especially Zarev, they're doing that job. They're recovering particularly these partially wrapped Fukaya categories.
Are these theories supposed to be Z graded or Z2 graded?
Ooh, they are graded by Z central extensions of the first homology of the surface, which in general is non-abelian. Now you do have, if you are fine with Z mod 2 gradings, then you can get an absolute Z mod 2 grading that then you can combine that with the intrinsic grading by the first homology of the surface, and that will give you a Z mod 2 homological grading, and then like a grading by a larger abelian group that's sort of intrinsic or quantum in some sense. But if you want that Z mod 2 to actually be a Z, then it can't really be disentangled from the other component of the grading, and you have to deal with these group valued things.
And in your story with Raphael, do you want a Z graded story or Z2 graded? What's natural for you?
In what we have on the archive right now, it is that's one thing that we left for the future, but we're trying to work that out, possibly for a V2 of the archive paper. That's actually what we're working on right now, is getting the gradings, sort of these general group value gradings, getting a version of the tensor product that works in the right way with those things. And yeah, in some settings, it's easier, like you have just a Z homological grading and some quantum grading or something. And then in those settings, the tensor product is fine. You can do graded versions of that. But to actually get these non-abelian group things, yeah, that's sort of one thing that we're trying to work on right now.
Trouble disentangling the homological Z grading from the H1 of the surface?
Well,
the grading is of the surface.
Well, they sort of have to be sort of messed up with each other in a non-abelian way. Like you can show that there's no Z grading on these algebras such that the usual basis you use is homogeneous. And well, maybe there's some other Z grading, but somehow this is always viewed as a no-go result. Like you can't, there's no Z homological grading on these algebras that's going to do what you want it to do. And because you can just get a contradiction, even in the simplest case for like say an interval with these two linked matching arcs, like I showed. If I look at that algebra sort of comes into three summands, and one of them is like the standard example of there's no Z homological grading on that. So it's impossible to disentangle them, but still you can try to come up with a formula that like produces a bigger group valued grading from smaller ones. That's more or less what Douglas-Manolescu do, and we want to, well, we want to say something like what they do, but also just like, I mean, we need to phrase it in different terms. It's not entirely clear how to do it. So yeah, that's why hopefully we'll get this resolved soon.
Does this issue arises only when you start? It's funny. I see. So you'd say that this is a feature of the whole theory, not
Yeah.
necessarily of the one with borders and sutures and so forth, right?
Right. Well, it's a feature of any bordered Floer theory, starting with Lipschitz, Hochwald, Thurston, and 08. Like anything with these.
I mean, I certainly agree it's not obvious how to put a Z grading, but you claim it doesn't exist.
Yeah, that's like in their paper. They'll I forget the like, yeah, there's like a warning or something that like shows that there's a proof that there can't be. I mean, it's hard to prove that there can't be a Z grading overall, but I think the proof is strictly that there can't be a Z grading such that the usual basis you use consists of homogeneous elements.
Okay, great. Thanks.
Okay. Good. Okay, so this is just a comment on why this is more or less this way of viewing things is compatible with what we've said so far. But often this sutured structure, especially if you're going to look at sutured surfaces and these lambdas and S plus and S minus, sometimes people take the following opinion, which is a valid opinion, is that, well, maybe we should be looking for a more geometric type of TQFT axiom that's really based on sutured manifolds or even whatever the geometry suggests, right? And that this overly rigid categorical perspective just isn't doing it for this type of theory. And that can lead to very interesting definitions. I don't want to say anything negative about that type of viewpoint whatsoever. I just want to propose a different type of viewpoint in which this sutured structure is taken to be just the presentation of a surface or a three manifold as some sort of higher morphism in a cobordism category, more or less compatible with the things that get assigned invariance by the well-structured types of TQFTs. Okay, and to talk about this and the connection with the work with Raphael, I want to, well, bring in the sort of last bit of Heegaard Floer lore that I'll talk about, this cornered Floer homology business. So if bordered Floer was really, it says it's about cutting up a three manifold along a surface, but in actuality, you were really cutting up a Heegaard diagram along a one manifold. Well, cornered Floer will just go one step down and say it'll talk about being about cutting up a surface along a one manifold and recovering this A of Z, or this Fukaya category of symmetric products, from smaller things associated to the pieces. But what it'll really be about is cutting up this one-dimensional representative of the surface along a zero manifold, because just like with bordered, cornered Floer is based on making another transverse cut. At no point in any of this theory do I say, and now I'm going to generalize my Heegaard decomposition so that it's an arbitrary decomposition. You always have this extra Heegaard decomposition, so that if cornered is sort of about going down to one manifolds, what we would hope is that it's based on some ansatz about what's assigned to a point. And that's the sort of story I want to tell. So this cornered Floer thing it's not as well studied as bordered. Douglas-Manolescu wrote the first paper on it in 2011, and then there's a follow-up paper with Robert Lipschitz a few years later, and it is based on this make another transverse cut philosophy. So in this picture, this whole genus 2 surface that I'm drawing, that's the orange surface from before, okay? And in terms of the old Heegaard surface and the manifolds, I'm just drawing that orange circle. That's all I remember from that. And now, but like I tried to maybe poorly indicate with the previous pictures, if I draw this orange surface, I sort of remember from the intersections with these red 2 handles, I sort of remember these arcs in the surface. And that's what I'm drawing as these red arcs. But anyway, so I have this surface, and in the old view, it has this base point. And now I'm going to make another cut. Again, the cut must go through the base point. And to match with the pictures that Douglas-Manolescu and Raphael and I draw, we're just going to sort of tilt this over. So we're going to look at a cut like on this second type of picture, like this one right here. And So that's again, that's sort of the Heegaard surface cut was that orange circle, and this is transverse to it. And fundamentally, the orange and green circles intersect in a zero manifold. And okay, so, but they do, Douglas-Manolescu and Douglas-Lifshitz-Manolescu, they do things this way with point and match circles and cutting through the base point. They don't try to do the sutured thing, although one could, and that's going to be the sort of first lead into this thing with Raphael. But how they view it is, we're going to be taking, like if I just look at what's going on with the orange circle in this second picture here, the orange circle with base point being cut by green things, it basically looks like it's being cut. The thing on the right is being cut to give the things on the left, or dually, the things on the left are being glued to give this right thing. So what cornered Floer homology, as currently formulated, says is we're going to recover the algebra of this point and match circle on the right from some pieces, some stuff associated to these two pieces on the left. And what stuff? Well, because the pieces look weird, well, then it's sort of like, well, it must be some new, and they do indeed define some new algebraic gadgets that are associated to these pieces. And then there's a sort of gluing formula for gluing these new algebraic types of things that produces a DG algebra. And then they prove that that algebra is A of Z if you glue things like this. So, and it just really does look like we have a zero-dimensional manifold, really points, and really gluing one manifolds along points. But then it's not just gluing along a point, it's gluing along 2 points, one of which is a base point. So if you're going to really try to push this idea about Heegaard Floer being about looking one dimension down, if you're going to try to push that to the extreme, and you take this viewpoint on cornered, then it looks like, well, they were assigning something to 2 points, one of which is the base point. And that is not how things are supposed to work. Okay, so, well, this is sort of where the story lies in the literature until this paper with Raphael, which doesn't really fully sketch out the alternative to it either. I'm trying to prepare something in the next few months. But to make progress beyond where this lies here, it's good to look at the representation side. So one thing that you do with these algebras A of Z is you say, well, look, I'm gonna.
So the algebra A of Z is a known quantity?
Yeah, algebra A of Z is a relatively easy thing to define from any of these diagrams. You can define this thing with pictures, and the gradings are complicated, but like the definitions are, you gotta get the details right, but like, yeah, it's basically a known quantity.
So if I give you a Riemann surface with all this data, you can, or these kind of graphs you're drawing, you can write down the algebra for us.
Yes, exactly. Yes. And that's sort of, I didn't do it in this talk only because, yeah, it's.
And is it known that algebra is supposed to be, I mean, basically equivalent to the Foucault category?
Yep. That's the result from Maru's ICM address. That like it's strictly speaking this partially wrapped Foucault category.
I see. So from his paper, I see it just follows. It's all the same. Yeah.
I mean, strictly speaking, he sketches the proof there, and it's, according to people I've talked to, it's now completely fine due to work in the intervening years on partially wrapped Foucault categories that have sort of really solidified that theory. But yeah, as I understand now, that's treated as just a perfectly good theorem that these explicit algebras defined in this bordered way give you this concrete description of the Foucault category, these partially wrapped.
Right.
Okay. So, but these A of Z's that describe Foucault categories, they also often take categories of modules and then try to decategorify in whichever way you prefer. And often these can be used to categorify representations of quantum GL11. And I have a paper on this with a theory of Ochoa and Sabo. There's work of Ellis, Pekka, Van Berge. There's work of Yin Tian, Sartori's work on GL11 categorifications is related to this. And so there's this thing called the vector representation of GL11. It's a two-dimensional vector space that's acted on by 2x2 matrices, but you treat it as a super vector space, one even, one odd generator, and the matrices are given the super commutator. So this is GL11. There's a quantum version where there's, the action is basically still the same, but you have this quantum group acting. And so, okay, so you have, for instance, diagrams Z. Say a family of diagrams Z that depend on some parameter n. And then if I fix an n and I build the right category from A of Z, then that's going to categorify this particular tensor product of the vector representation with itself n times v to tensor n. And well, on the other hand, I can look at least for some A of Z's, particularly the ones in Yin Tian's theory, you can use the idea of cornered to cut up the diagram for n things into like a repeated sort of gluing of smaller diagrams for n equals 1 that just categorify V. So cornered in general, although the way Douglas-Manolescu have the theory set up, it doesn't really allow for iterative gluing, but still it looks like this should be applicable here. And on the other hand, there's another thing that does exactly this, and that's Rouquier's work in preparation on tensor products of higher representation. So if I have some categorification for just V itself, and I have the right sort of 2 action on that, then I should be able to start tensoring that categorified thing with itself with the categorified tensor product operation and build a categorification of V tensor n.
And
So
that's supposed to be gluing of categories?
In some sense, yes. Yeah, the cornered especially should be like gluing the Fukaya categories. And then if you, well, these, yeah, so that's what our theorem says, is that these things, this tensor product, we define a variant of this general thing that Raphael will define for Kac-Moody algebras. We define a variant for the positive half of UQ of GL11. That'll be the next slide. And then the theorem is, well, okay, maybe I'll just do the next slide. Oh, wait, I have 1 second to next slide. Yeah, so that's right, though. The theorem is going to say that this tensor, that the algebra of a larger Z is the tensor product of the algebras of smaller Z's. So that's saying basically the Fukaya category of a larger surface is some sort of tensor product of Fukaya categories of a smaller surface, but you have to be like, which type of decompositions of a surface are we looking at? There's a lot of different ways you could think about cutting a surface. There's like Haydn, Katsarkov, Kontsevich way of thinking about decomposing surfaces. This is a different way of thinking about things, different types of decompositions. But yeah, so
there's a specific way that Vivek thinks about, which I think is the right setting here. I mean, he would literally, I think, glue, 3 punctured spheres in the most obvious way. I think that should be right.
Yep, and that's, as I'll try to argue, that's like very close to right, although it's just a slight variant on that is what I'm proposing. But so to talk about that, it's useful to say, well, what happens if they hadn't, if they, when they were doing this cornered theory, if they had used bordered sutured instead of bordered, okay? What if instead of doing this type of gluing, they wanted to do the bottom type of gluing? Okay, this somehow to me looks a lot more natural. The pieces that are being glued are no more weird than just your standard arc diagrams. And in general, so this type of gluing would be like, I have 2 arc diagrams, each of which have a distinguished interval component. Maybe they're not just a single matched interval, but maybe they're a bunch of stuff, but you have a distinguished interval component on Z1, same on Z2. Then I glue the distinguished components together to get a new interval and call this resulting diagram Z. And this new interval is distinguished on Z. Okay, so this type of gluing, now we can say some things about this. So first, the sort of stuff that Douglas-Manolescu defined for like these top and bottom pieces, the sort of weird looking ones here that I'm trying to circle with my cursor, those, well, we repackaged their new algebraic constructions for those things into the following data, is that if I have one of these arc diagrams Z with a distinguished interval component, then I get a 2 action of this DG monoidal category U on the algebra. It's a 2 action by like bimodules and bimodule maps for this monoidal DG category. And with this U thing is a categorification of the positive half of UQ of GL11. So it's like for each remember the interval components of Z were the same as the interval components of S plus in the sutured surface, okay? So for each interval component in either context, it's like I have an action of this U on my algebra, and it could, or on the category of modules over it if I want, okay? And then there's this operation that takes two of these things, two of these two representations, just like this thing that took V and V and produced V tensor 2. There's a similar operation at the categorified level. It takes a two representation of U and another one, and it tensors them together to get a two representation of U. And then if the way this is defined, it's more or less a tautology that if I take Douglas-Manolescu's gluing formula and I reformulate it in these terms, what it's saying is that the algebra of the glued together thing, glued to end, is on the nose up to DG isomorphism and not even homotopies or anything. It's this tensor product of the two representations for the two pieces. And Douglas-Manolescu's result says that as DG algebras. But in fact, this tensor product construction, the result of that comes with its own two action of U. And what we say is that, well, the two action that comes from the distinguished interval of the glued thing, that's the same as the two action that's built abstractly with the tensor product. So this isn't just an isomorphism of DG algebras, it's an isomorphism of two representations of U. And this is highly suggestive in my view. One thing it does is it says really this bordered sutured perspective, I mean, it at least supports the bordered sutured perspective over the other one. The reason is that when I glue two of these arc diagrams and get another arc diagram, I mean, the result is the same sort of thing, okay? Everything is a two representation of U. So in Douglas-Manolescu's theory, you only got the extra structures that corresponded to a two action when you had like half of a pointed match circle. But when I glued and had a pointed match circle, then it didn't seem like there's any extra structures that should have. But we're saying, well, no, that has equally natural extra structures on it. That to us really means that it's not actually a pointed match circle. It's this diagram, it's this arc diagram, the interval that geometrically this has a distinguished interval just like the two beginning things did. So from that point of view, yeah, gluing arc diagrams looks a lot more like this tensor product operation does than gluing halves of pointed match circles does not look like this tensor product operation. And a related way to say it is that, well, here's Douglas-Manolescu's picture of what their gluing looks like on the level of surfaces that we briefly drew a little bit above where we tilted this picture. And ignoring the extra data, it's sort of two surfaces being glued along a common S1 boundary, and then that boundary gets eaten up and the resulting thing is closed, maybe with a base point or something. And algebraically, this type of tensor product looks like, you know, there's a topological sort of gluing that usually gives this type of tensor product. And this is, or sorry, there's an algebraic type of tensor product that usually corresponds to this topological type of gluing. That's what I should say. And that is if I have like a left module and a right module and I tensor them together and then the result is just an abelian group. Okay, and so the algebra action gets eaten up. It sort of can go back and forth, but it's stuck inside the tensor product. And, you know, that's the algebraic type of tensor product that corresponds to the gluing shown in this picture. But there's another type of tensor product, and that's the one that was really V tensor N, you know, is the second type where I have a Hopf algebra, not just an ordinary algebra ring or something, but a Hopf algebra with a co-multiplication. Okay, and now if I have not a right module and a left module, but if I have two left modules, I can tensor them over the ground field. Well, I could always do that. But if my algebra is really a Hopf algebra or has this coproduct, then I get an action on this M tensor over K with N. Namely, if I have an element of H, then I'm going to apply the coproduct that sort of splits it into two elements, and then one of them acts on the M factor, the other acts on the N factor. So this is a different type of tensor product, and it has a different sort of topological interpretation. So this is the one where you have like these pair of pants type of gluings, like this. So if you see a tensor product that is looking like this second type, where it's like tensor product of a Hopf of representations of a Hopf algebra, then topologically, what one is usually expecting is not these sort of glue two things and eat up the boundary, but rather it's like gluing into a pair of pants type of thing. I have two things glue into the two legs, and then I get out. So I start with two things with circle boundary, and I'm left with another thing with circle boundary. That's what this second type of tensor product is usually like. And the Raphael style categorified tensor products that we're using, and the V tensor N type of constructions that we're talking about, it's all this second type of tensor product, not the first type. So if our theorem is saying the Douglas-Manolescu gluing is algebraically given by this second type of tensor product, then you'd think, okay, topologically, then it should be given by something more like a pair of pants gluing maybe than what Douglas-Manolescu say about it. But at this point, now we bring in the final sort of complication and get to the real proposal here. Is that, well, we know what our gluing is doing because we know what happens when I glue, I have an arc diagram that represents some sutured surface. I have another arc diagram represents some sutured surface. I can glue the arc diagrams and look at the resulting surface there and just ask how that's obtained from my original ones. I just want to draw a couple ways of visualizing it. I could say, okay, I have the orange S plus boundary, and then the black S minus boundary. And this came from my distinguished interval on bottom. And then on top, I have this little bit. Now I'm going to glue them end to end, and I get this type of gluing here. That's one way to view it. Another way is, well, I can think of the sutured surface as being a cobordism, which is sort of a cobordism with corners, from S plus, a one manifold with boundary, to S minus, another one manifold with boundary, or vice versa. And it's sort of, what I'm doing there is really taking these sutures, which are points, and I'm extending them out into intervals, okay, so that they stretch from the input of the cobordism to the output. And then if I view my sutured surfaces like this, then the sort of gluing that results from the arc diagram gluing is just like gluing along. It's like it used to be gluing along a suture more or less. Now it's gluing along like this interval that got extended out from the suture. But probably the most informative way to think about it at this point in the talk is it's more or less gluing an open pair of pants rather than a closed pair of pants. That's topologically all three of these things. If you look at an example or something, it's maybe easier to see, but all three of these things are the same, or they have the same effect on sutured surfaces, all three of these types of gluing. And this is the effect of our end-to-end arc diagram gluing. So this looks like it's very much like this closed pair of pants gluing, except everywhere instead of thinking we're associating something to a circle, it's really to an interval. And the tensor product really comes from open pair of pants gluing rather than closed pair of pants gluing. And specifically what's being associated to an interval, like an interval in S plus, that corresponded to an interval in Z. And that is an algebra with a two action of U. So what it looks like is going on is that this two category of two representations of U is being assigned to an interval. And then if I have some object, that gives me some two representation for one interval, another object for another interval, then the tensor product construction comes from gluing into the open pair of pants. Okay, and one thing about this is that this U business, it really categorified the positive half of quantum GL11. And so usually I think of something related to the full quantum group being assigned to a circle. And if you ignore all details, the full quantum group is kind of like the double of its positive half. And usually the circle invariant is the double, Drinfeld double, Drinfeld center, whatever, of the interval invariant, if I had, say, a fully extended thing. So assigning something related to the positive half, assigning that to the interval makes at least sense mod details. And one thing to notice, the closed pair of pants is a perfectly good morphism in the 1, 2, 3 cobordism category, but or even in the 1, 2 cobordism category, okay? if I have the closed pair of pants. But this open pair of pants, if I look at this bottom picture down there, that is not a morphism in the 0, 1, 2 cobordism category, but it is a morphism in the open closed cobordism category. So if I wanted to think this was all based on fully extended TQFT and going down to a point, I might think, well, that's not good. But in fact, a fully extended TQFT would give you open closed TQFTs by a more or less standard type of construction. And what would happen then if I wanted to assign some invariance to this open pair of pants gluing in item 3, it would more or less amount to reducing it to item 2. So that through this convoluted explanation, here's what I propose. Here's what we propose. We take 2 representations of U, that's a 2 category. We give it a monoidal structure from this tensor product. Okay, we know how to define that on objects right now. We'd want a more homotopical version with a good definition on A infinity morphisms. So we'd want all sorts of stuff. But here's just a toy model. You take this should give you a monoidal 2 category, and that can be viewed as a 3 category with 1 object, and you're going to try to assign that to a point. That is the sort of proposal for the Seiberg-Witten invariant of a point. And then if you did that, what would happen to an interval? That would get assigned this point invariant, but not as a monoidal 2 category. It would get assigned, well, just 2 rep of U as a 2 category with 2 actions of itself as a monoidal 2 category. So it'd be like a bimodule 2 category over itself. But fundamentally, it would get assigned the 2 category 2 rep of U. Okay, now what would happen if I had 2 intervals and each of those intervals gets assigned 2 rep of U. And so if I have
sorry, it's a bimodule because it has an interval has 2 ends?
Exactly. Yep. And so now if I had 2 of these intervals, and each of them gets assigned this 2 category of 2 reps, I'm going to suppose I have an object of each of these, and then gluing the intervals should give me some object of 2 rep of U, in which one, if I assigned this particular thing to a point, then it would be this tensor product. So that already this sort of proposal for the point seems kind of compatible with the end-to-end type of gluing, that this end-to-end gluing of intervals should be something that's corresponding closely to the tensor product. You could ask in this frame, before going to surfaces, which we'll do next, but you could ask in this framework what gets assigned to the circle. And because that's how, that's a very common question. The answer is, well, nothing that I know about yet, something, some sort of, right now I just want to say, let's suppose it's 2 rep of some sort of Drinfeld double of U, but that's not something that I've seen appear in the literature. But still, let's talk as if this D of U, this double of U makes sense, and that 2 rep of it gets assigned to a circle, right? Then let's look at what happens to surfaces, okay? So based on what I really briefly stumbled over before, the answer is...
And just to make sure I didn't misunderstand anything, the object of your 2 category is still a brain of the Foucault category, right?
The object of your 2 category, no, it's like the Foucault category itself. It's like
it's the Foucault category itself. Okay.
Yep.
Okay. All right, sure. Okay, and to this, it's the Foucault category itself. Okay.
Yep. Right. And that category then has an action of it, a 2 action of this U thing. And
because in the Heegaard Floer world, you're increasing, for example, the K of the sim K.
Yes, that's what that action would do. Exactly. Good. Okay. So, but then the upshot is, so I promised that I would say this weird looking sutured structure that would get interpreted as some sort of morphism data in a higher cobordism category. Well, for sutured surfaces, precisely what I mean is that if I can view, if I take the sutures lambda and I extend them out to intervals, I'm going to get some surface with corners then. And that surface with corners, I can view that as a cobordism. It's like a 2 morphism from S minus to S plus in the 0, 1, 2 cobordism category. So S minus and S plus may themselves be morphisms from like some collection of points to some other collection of points. But my sutured surface viewed in this way, it's like trivial along the boundary of the boundary, which is what you need to be unlike this open pair of pants that we had before, which did not give a two-morphism here. This way of viewing the sutured surface does give a two-morphism. And so then you can ask, well, what would a fully extended TQFT assign to that? And the answer would be something very complicated. That's more complicated than these strands algebras A of Z. Something like a two-functor from a domain two category for S minus. It's going to be maybe some tensors of 2 rep of U a bunch of times, 2 rep of D of U sometimes, and then a two-functor from that to another thing, and then somehow compatible with whatever's going on at the boundary, okay? Well, for instance, if S minus and S plus were a single interval, maybe this surface would give me a two-functor from 2 rep of U to itself, okay? That's maybe compatible with the boundary somehow. And well, maybe one way to get such a two-functor would be if I had a category that had 2 actions of U on it, okay? And then I start with 2 rep of U, so that's like categories with an action of U or algebras with an action of U if you want. Let's say categories with an action of U, and then I tensor with this bimodule category with 2 actions of U, and then I get another category with an action of U. So that's the sort of thing that maybe could get assigned to such a sutured surface. And in general, okay, that was just the case if it's like a single interval to a single interval, but in general, maybe you'd expect that to a sutured surface, you'd assign some category that has a bunch of different actions of either U or of D of U. You know, if I have interval components in S minus and S plus, those would give me 2 actions of U. And if I had circle components, those would give me actions of D of U, whatever D of U is. And then perhaps you hope that this category is like modules over some DG algebra associated to the sutured surface, such that DG algebra for every interval component in S minus and S plus and every circle component in S minus and S plus, it would have actions of these U and D of U things, 2 actions of these things. Well, let's call that A question mark of Z, because that's too big. You can show heuristically that A of Z, if that A question mark exists, A of Z is not big enough to be it. Okay. On the other hand, here's one thing you could say. Let's go do some more hypothetical things to the hypothetical question mark algebra. Let's suppose that we had this thing and everything made sense and the heuristics are valid. But then in these heuristics, what I'm going to do is if I see, first of all, anything, intervals or circles in S minus, I'm going to assume that I sort of paired those, I tensored those with the trivial 2 representation of either U or D of U, so that I don't actually have any 2 actions anymore for any intervals or circles in S minus. And then I'm going to go to S plus and do the same thing for the circles, okay? So I'm just going to kill off all of the 2 actions of D of U by tensoring in some sense that I don't know how to define or even really think of in the right way yet, but the heuristics that I'm using for counting idempotence and stuff like that, it makes sense in those terms. And so if you kill off all of the circles on the S plus side and all intervals and circles on the S minus side, then you should get maybe a double question mark of Z, some algebra, which then you have some heuristics for how many idempotents it should have, and the answer is then the exact same number as A of Z. So that's the guess, is that's how I want to think of these A of Zs, is that it would be like the algebra that's really like a fully extended TQFT invariant of this surface almost, except that I tensored off a bunch of its actions with trivial representation. So it's really a smaller thing that was obtained from, right? So one could hope to try to build larger algebras like this A question mark and build more of this TQFT. But let's suppose if we had this stuff, then it would be true that this item 2 gluing, at least heuristically, but this item 2 gluing would give me the tensor. And then if I built an open closed TQFT, the open pair of pants gluing would give me the tensor product that we're seeing that it gives us. So that somehow everything we know about these algebras is more or less, at least at this level of ignoring details, which is going to be a big task to overcome. But at least at this level, it seems everything is compatible with this picture. So let's briefly say, and I mean, I was given a 1 to 2 hour limit, and this is 2 hours. So let me just, I have like 1 slide, 2 slides left. At 3 dimensions, you can say a similar thing. A sutured 3 manifold similarly can be thought of as a 3 morphism in the 0, 1, 2, 3 cobordism category. Same for Zarev's like bordered sutured cobordisms. Okay, so you can interpret the sutured data as being higher morphism data. And so it's not really this weird thing that's different than the standard TQFT framework. It's really very similar to it. And then the expectation, if all of this was optimistically true, you'd expect that there's some 0, 1, 2, 3, 4 partially defined TQFT that assigns. It would have to be really a serious, vast elaboration of this. This 2-rep view comma tensor would really be a toy model for what could get assigned. This isn't realistic. It isn't a realistic expectation as stated, but it's hopefully the first sort of indication of the form the answer should take. Some serious elaboration of these ideas, homotopical and building in these group valued gradings, that's another key part of it, should be able to be a more or less partially defined but fully extended TQFT framework for Heegaard Floer homology. And this is something that even if I look down in 3 dimensions instead of 4, this is making some interesting claims about what could be going on in 3 dimensions in terms of TQFTs recovering the Alexander polynomial, being extended down to points, that sort of thing. So that's something that I want to look at in the relatively near future, makes use of ideas that are sort of at the modern edge of thinking about 3D TQFTs. It seems like this sort of thing would be an interesting, is sort of at that level like of difficulty. Hopefully would use some modern ideas in a nice way. But there's something that's even easier, and that's sort of if I think about decategorifying twice, then actually you get something really nice. Is that there's just a fully extended 2D TQFT oriented. And this is rigorous. This now without
what
3
does it mean to
manifolds.
decategorify twice?
Well,
I guess
heuristically. So for me, it means I have these algebras, and each of them has a certain number of basic idempotents. Okay, and decategorifying once, well, by that I mean I'm just going to take the vector space spanned by those idempotents, and decategorifying twice means I'm just going to take the number of those idempotents, and I view it as part of the that's definitely a question, because decategorifying via K0 versus by compactifying on a circle, these are different things, and compactifying on a circle, well, I would need to know how the full theory is defined on, say, 3 manifolds to be able to decategorify it that way, but I'm not really trying to do it that way. So yes, in a very heuristic sense, and this is where these heuristic dimension counts come from. So the rigorous thing is that there is a fully extended 2D TQFT that's very easy to describe, although I don't want to give spoilers right now because I'm going to write a paper on this very soon. But there's a very easy to describe 2D TQFT that, well, I can't prove anything about its relation with these hypothetical categorified theories, even once categorified here, but I can say that if I extract numbers from this 2D thing in the way that this picture would suggest, these numbers are exactly the number of idempotents for these bordered strands algebras. So that, yeah, to me, that seems like that's the simplest thing you could do. And then at least, it's epsilon piece of evidence where I don't really have any evidence yet that like this, that this is somehow missing something. I mean, there's a lot that is missing, but like, it seems like stuff that could be added in my opinion. It'll take a lot of work. So like this decategorified, twice decategorified level, like probably, yeah, I write a paper on like 2D TQFTs and then try to say something about 3D TQFTs and, like be motivated by what I have these optimistic dreams about, but in terms of actual
what
stuff.
does the number of idempotents mean from GL1/1 perspective?
That is like the dimension of the representation. So if I have this A of Z that categorifies V to the tensor N, well, then the number of idempotents in this A of Z in all of these cases will be 2 to the N.
I see. Okay. I see. So your 2D TQFT is computing that.
Yeah, it's computing those. In general, there's some like topological formula for, based again on the first homology of this surface, but the topological formula for this number of idempotents. And you can see it, but like the nice thing about this is like you can see exactly what you need to do to get the right number of idempotents. You write down this 2D TQFT, and it looks like, at first it looks like, oh no, the number is bigger than the one I have. But then you realize that really I'm supposed to be labeling away all of the S minus things and all of the circles on S plus. And that in some sense explains something that Raphael and I have been wondering about for a while, is that why, when we're doing these things, do we only see two actions of the positive half? And only for intervals. We don't see any sort of two actions whatsoever for circles, not of something bigger than the positive half, not even of the positive half. And from this point of view, that's because, from even looking at this simple 2D thing, these A of Z algebras with their number of idempotents, they're really supposed to be giving things where any action for a circle has already been killed off. So that is the end of the talk. But I'm definitely willing to take questions. I realize this was, so I want to apologize if you thought this was vague or sort
No,
of.
it was great.
There are like more standard talks that I've given on this that I'd be very happy to share slides with if anyone is interested.
Okay, do we have questions? More questions?
Yeah, sorry, I may have one more question.
Okay.
Can you explain geometrically what is this AZ and this A question mark Z doing? Like,
right.
are they, the Z is like this arc diagram? And
yeah,
from
Z,
the arc
exactly.
diagram, you can cook up a sutured surface?
Yes, that's right.
How do you cook up the sutured surface from this arc Z?
Good. Yeah, let's go back to that.
I thought I understood, but maybe not. Like you had this picture where you have two holes on the surface.
Yep, exactly. I'm just going back to that one. Sorry. This is one of the other one that's better. This one's better, right? So, so what you're gonna do is you start by like thickening the arc diagram. The way I'm drawing it, you have like the orange part and the red part.
Yes.
The red part is just these matchings, so you don't even like the arcs are kind of heuristic. But I have the orange interval here and an orange.
Sorry,
circle.
so can you say again? The black arc. The black arc is the matching of the.
Oh, sorry. The red arcs on this leftmost picture here. The red arcs just indicate which pairs of points are matched.
Okay.
But it is also sort of geometric that you have arcs there, because what you're going to do is you're going to thicken the orange part. So they'll just cross the orange part with an interval. And then I can already put on this sort of sutured data, like I put one side orange, the other side black. But if it was an interval, those need to interface along 2 points. And that's where I get sutures from on my boundary of my surface, is when I had an interval. So like the number of sutures overall, the number of like green dots in my boundary of my surface will always be twice the number of intervals in my arc diagram, because that's how I get sutures, is I thicken this and I add the sutures.
Yeah, I guess the interval is new to me. Like without the interval, I would just put the ribbon around the orange diagram. But with the interval, somehow you get circle with black part of the boundary.
Yeah, exactly.
I don't quite see that. But somehow the black part, even though on the middle part is quite long, on the right part, on the right,
right, it's
yeah.
If I trace that through, that's a single arc. Okay, and that's like this. I guess this is like one of the more standard, from bordered Floer homology. This sort of like two nested arcs presentation of a genus one surface is just like something that we were trained on from early grad school. So I apologize I should explain that more. This really is the same thing topologically. So I build it, and then you can, for me, it's easiest to think in terms of classification of surfaces, right? I build this complicated thing, but what I'm going to do, count its Euler characteristic and look at its boundary. And check its
yeah, I think I can buy that. So another question, your S minus and S plus, which one is which?
Orange is S plus and black is S minus, and that's Zarev's conventions.
And you want to view this as a Bordism from S minus to S plus with this surface.
Yes.
But you, and what does the connection, this arc connecting these points, this orange arc, what does that mean? Like, are these skeleton of the surface, or are they like coming from an intersection from another surface?
I think those are actually red arcs. Are those the ones?
Yeah, the red arcs.
Yeah, those I can think of as, so I got the surface from, okay, I can think of that in several ways. I can think of them as giving me a bunch of Lagrangians in the surface that I can take products of, that then it gives me Lagrangians and thus objects in the Fukaya category, and correspondingly idempotents of these algebras. And so that's where.
So these are like the union of, like, you want to think these orange arcs like the unions of Lagrangians, or partially Lagrangians, like a part of the picture.
I want to think of this like the red arc is itself a Lagrangian in the surface, and it goes out to the boundary. And if I wanted to take a Fukaya category, I would want to do wrapping near the boundary, and then I would wrap. So like the red arcs are always going to end on orange, and I'm allowed to wrap around orange. But if I hit the black S
Wait, there's orange and red? I thought there's the same color.
Yeah, sorry. I could have picked better colors. I was trying to follow the colors from Zarev's thesis, but yeah. So there's like the orange and then red. And the red ones are like transverse to orange.
Okay.
In this picture.
Yeah, maybe I would just go back and read more. Thanks.
I mean, yeah, I'm sorry. I didn't really do a good job of explaining this. I'm trying to do a whole bunch at once of just like trying to sell this perspective on stuff and try to make it make some sense, but then I have to go kind of.
I mean, that's great talk. Thanks.
Thank you.
So the thing okay. The others have questions? I have one more question, I suppose. Okay, if there are no other questions. So the one aspect of the story that maybe I didn't understand, right, is both in, so from our perspective, these theories come from, well, the GL1/1 had conformal field theory.
Yep.
Or equivalently also in the Heegaard Floer theory itself, the K of the symmetric product is in one way or another tied to the genus of the Riemann surface. So from that perspective, it would seem to me that the most obvious gluing is actually gluing over a circle that with nothing on it whatsoever. So you just cut out a little hole, and you glue a Riemann surface of genus G1 to a Riemann surface of genus G2 with its entire structure, and we can have that. So why is that not natural for you?
That's just sort of, that's right. So I would say that's because of the existence of base points / sutured structures, which in the Heegaard Floer realm are always necessary to sort of get off the ground. Like you always, like that. Sometimes people try to phrase the theory as not depending on those things because it sounds better if it doesn't. But what I think, or at least what I'm proposing, is that there's this whole other sector of things that Heegaard Floer hasn't looked at, and that there very well should be an invariant of a circle, and there very well should probably be invariants of a genus G surface with plain S1 boundary, and that's entirely an S plus, okay, or entirely an S minus, and it's not sutured in any way. Okay, and then there should be some like a question mark type of thing that, and then this sort of thing should get assigned some algebra that's like bigger than the strands algebras you might have. You know, if I had maybe some other part of S minus elsewhere, I could represent this by an arc diagram and get some algebra for this surface. But you'd really hope that there's some new algebra that's like got 4 times as many idempotents for every circle, basically. And that it's, well, then here you would have this 2 action of this double of U, whatever that is, and then gluing along, taking a tensor product along that should give, yeah. So it seems like there's this whole other side of things that maybe the people who work on Fukaya categories, I think maybe, because for them it's very natural. Okay, what happens if we don't have any stops at all, or those sort of questions. Whereas in Heegaard Floer, To me, it seems a little bit like the emphasis on trying to do everything with just base points, close manifolds with base points, and then shove the base points under the rug has led to less of a focus on this type of questions, as far as I'm aware.
And your perspective is geometric or algebraic or both?
I would say right now it's very algebraic. It's very much like we have this tensor product, and it suggests certain things from like the way the algebra of these extended TQFTs usually work. And it would be really great. So, and I know this is something Raphael would think is really great too, is the more of this that can be understood geometrically. I mean, he wants to think of this tensor product construction fundamentally as being related to constructions of moduli spaces in algebraic geometry, which would be a really great, like if you could, I think that would be sort of like a geometric way to think about, I think, and he has interpretations like that in general. I think in the Kac-Moody setting, I should, if I asked him, I may not understand his answer, but like he said, like we say this in the introduction to our paper, he wrote that, not me, that bit about moduli spaces, but yeah, so I think there should be geometric things, but the way I think about it, at least, it's very algebraic, at least at this point in the game.
Yes. And maybe you've said this. If one wanted to do the same thing for SL2, this is already understood, or it's open, or?
Now, well, I would say this is like work in prep. This is like Raphael, okay, he's going to write it about the whole Kac-Moody case, but even if he did just SL2, it would still be an interesting paper because that's not in the literature, this sort of tensor product construction. This is sort of the first instance of this. And in some sense, this one for you, it's like a bunch of miracles occur and things that had to be A infinity, and even in SL2, for instance, don't have to be A infinity and just work up to DG on the nose isomorphism. And that's one of the really nice things about this project and like why that sort of set the scope for this paper. We're just going to talk about those things that don't require homotopies or A infinity.
Yes. Excellent. Thank you so much. This was a really wonderful, wonderful talk.
Yeah, thank you all. Yes,
it was a lot of fun.
Well, I'm glad you enjoyed it. I hope it wasn't painful. I hope it's you can now go enjoy the rest of your Monday afternoons. And
Great.
I'll do
thanks
the same.
so much for joining us, and thanks everyone.
Yeah, thank you very much. And yeah, hopefully I'll talk to some of you soon.
Okay, great.
All right. Bye.
Bye-bye. Bye, everyone.